So what we're going to do in this example is look at the equivalent of the paired t-test. So that's our Wilcoxon test in the literature, it's how it's referred to, but in R we know that it's going to be just an application of the Wilcox dot test function. So this is the same as the paired t-test. So in any scenario where we can conduct a paired t-test, we can always conduct this non-parametric equivalent. The difference is that this one also works when we have a small sample and non-normally distributed data. So remember, paired t-test, it doesn't rely on the population being normally distributed, but if the population is not normally distributed, it does rely on having a relatively large sample. And if we don't have a normally distributed population and we don't have a relatively large sample, we have to worry about the validity of conducting a paired t-test. So when those circumstances arise, we conduct the Wilcoxon test. Okay, works the same way, works on the ranks of the data. There is a test statistic called a capital T statistic, so not a small t. So student's T is the lowercase t, this is a big T or uppercase T. Conceptually, it's quite easy to understand because we're looking for the ranks in the data. So if it clusters, if the differences cluster at one end, we know that that's a sign of a difference. We have a formal metric to decide, what level of clustering at either end of the tail is sufficient to detect a difference. Our null is going to be group A is the same as group B. Okay, so we're not saying anything about means. That's probably the biggest thing to get your head around in terms of setting up the null and the alternate for these things. So again, really, it's easier to understand these setups if we look at an example. So here again, relatively small sample, bare hind legs and forelegs. Something about I'm interested in, the way they can catch salmon. Something biological that I'm interested in here. What do I do? I've got a paired sample. So regardless of whether we have a paired t-test or we have a non-parametric paired test, we're going to have a horizontal box plot. So first step, giving us our plot. So this is a plot of the data, not of the ranks. So we're going to ultimately work with the ranks for our test, but this is giving us some indication of what the data looks like. And I can see from this in calculating the differences that a lot of the differences fall on one side of 0. It's not exactly the case that they all fall clearly on one side, but many of them do. So that might be evidence that we actually do have a difference between hind legs and forelegs. And remember, I've measured them from the same animal, so they're paired measurements. So we look at a plot, that's our first part of any analysis. Next thing, set up our null and alternate. So hind leg is the same as foreleg. Hind legs are not the same as forelegs as the alternate. Alpha, always 0.05, so nothing new there. Calculate the test statistics. So again, R is going to calculate the test statistic and then use the test statistic to give us a p-value. And we're then going to apply the p-value decision rule to decide whether we should reject the null or not reject the null. All right, but how do we get that t statistic? And let's just look through the mechanics. So the first thing it does is it creates the difference series, okay? Then it creates the absolute value of the difference series. So we're looking at how far things are from one another, and then we rank these observations, right? And we're going to rank the positives and the negatives. So I'm going to use color coding to try and separate these out so it can become clear, hopefully, how the test works. Because the test is hidden in all the mechanics in R. It's nice to know how the test works. We don't want to do these calculations by hand very often, but we would like to know how they work. So I rank my first difference, gets a rank of 1. That's the smallest absolute difference, okay? So first of all, I found the differences. I've now found the smallest absolute difference, and it was a negative, all right? So that's blue. So my next observation is the next smallest absolute difference is 2, and it's a positive difference. So I'm going to keep track of my positive differences with red, and I'm going to keep track of my negative differences with blue. Right? And then the next one that I get to, I get a tie. So I have the absolute difference is 4 for 2 observations. So what are we going to need to do when we have a tie? We're going to need to give them half the ranks. Okay, so we find the average, they both get, it's 4 and 5, so they both get half, so they get 4.5 in my formula. And these differences were both positive, so I'm going to keep track of them with red. I then continue on. So my next observations, I have 5 observations. Sorry, at 5, I have 3 observations. So they fill positions 6, 7, and 8 in the rank order. So the average of 6, 7, and 8 is 7. So they all of those values get a 7. So you can see that you can end up with quite a number of ties in your system. And then the last 2 absolute differences are 6, and they are positive differences. So they're observations 9 and 10 in the rank order, and so they get a rank order of 9.5 and 9.5. So there I have allocated my ranks. So I've got all of my blue ones, they're my negatives, and all of my red ones are my positives. And I can see that, the larger ranks, so all of the, 7, 7, 7, 9 and 10, so the large numbers were where my positive differences clustered. So that's starting to give me evidence that actually there is a difference between these 2 groups. I then calculate my test statistic. So the test statistic is just the sum of the ranks, and we, for the positive differences, the sum of the ranks for the negative differences. We compare this to our critical value and apply our decision rule. So in the old days, so I would go to my statistics textbook, and if we had a physical lecture, you could see I've got these old school tables that I can look up. My critical value for an alpha, our alpha is always 0.05. We always conduct 2-sided t-tests. The sample is 10 and the critical value is 8. And similar to the other, our Mann-Whitney type test, because 4 is less than 8, we would reject the null and conclude hind legs and forelegs are different. So let's have a look at, and also similar to our test, you can calculate, you can use this guy or this guy in the way that you set up your tests. Okay, it doesn't matter. There's different tables that you can use. Anyway, that's how I used to do my, when I really did dig out these numbers from a book. I used to calculate this stuff in Excel and then look them up in a book. So, life is a lot easier for you guys than it ever was for me. Now here is my test with my data set, which is the bare data set. Apply the test. These are my 2 variables, and just paired is equal to true. All right, and so that's as simple as, we really know how to do this. It is our test. And you can see that it's given me it says this warning, can't compute the exact p-value. Well, I've looked at this in detail, and that the error is way off past the 3rd decimal place. So when you have these sort of tied ranks, yes, you can't get an exact p-value, but who cares? I mean, we're talking about the 3rd decimal place, and we're not really that interested in the 3rd decimal place. We've stopped at the 2nd decimal place. So in all practical, reality, this warning message, pretty pointless, okay? Yes, you can't get an exact p-value. The error comes up. I have, done these calculations as well. The error comes up at the 3rd or 4th decimal place, and we really don't care, okay? So what's our summary for us? Well, we just look at the p-value, we see that it's less than 0.05, we conclude that we reject the null, that the 2 distributions are the same. Okay, so forelegs and hind legs are not the same length. So what's our summary here for non-parametric models? So what do we need to know? For all parametric tests as a non-parametric equivalent, okay, when to use non-parametric tests, you use them when the assumptions of the parametric model are invalid. It's hard to know when they're invalid. This is something that you get to learn from, reading the literature. So you can't just, often just can't make a judgment on this. You have to be informed and read up on what's going on in the area. and we tend to find them in the natural sciences. So many other sciences, you won't see people consider these kinds of tests at all, just because they're not relevant, okay? But I come across students who do a lot of field work and get small data, like 8 observations, 12 observations. We're really unsure what the population shape is. Sometimes we need to revert to going for the non-parametric tests. How are we going to tackle non-parametric tests? Pretty easy. We've got some steps to follow. The first step is exactly the same as whatever we did for our parametric test. So we can have histograms and box plots, okay? If we have 2 samples, we're going to have a box plot. If we have a paired test, we're going to have a horizontal box plot. We're going to need to specify null and alternates. Group A is the same as group B, okay? Very, very general. So slight tweak, basically just deleting the word mean. And then we implement the tests in R and look at the p-value. I know that it is going to give us some warnings sometimes, but I also know that the warnings are not relevant for us because they bind at such a low level for the p-value. We just need to implement our tests. Depending on how your data is ordered, you might end up with a tilde sign or a comma. If you want a paired test, you just put paired equals true. And if it's a 2-sample test, you just leave that bit out. So that's our setup. It's as easy as that. So we understand how these tests work. They work on the rank order of the data. We've seen how to implement them. Our focus is on implementing them and drawing conclusions in R. What we haven't covered yet is that we can do single sample tests. Of course we can do single sample tests. We know that if we've done a paired test, that's exactly the same as a single sample test. So of course we know we can do that. But we will also look at some ANOVA tests and multiple comparison tests. Same corrections, same setup that we've seen in the parametric world when we go to multiple comparisons for our non-parametric equivalent. And that is an opportune time for a break.